Hello and welcome back to yet another podcast of the quest for quantum gravity, where we dive deep into the frontiers of science, explore the mysteries of the universe, and bring up to you conversation with some of the brightest minds shaping our understanding of reality. I'm your host, Shaunak, and today we have a truly exciting topic lined up: the quest for quantum gravity. I think it is one of the biggest puzzles in modern physics. How do we reconcile Einstein's general theory of relativity, which governs the cosmos, with quantum mechanics, which rules the microscopic world? To help us navigate through this fascinating journey, we are honored to welcome Dr. Diksha Jain from the renowned Cambridge University as our guest today. Dr. Jain's journey through the world of theoretical physics has been very impressive. She began her career at IISER Mohali, where she completed her BSMS with a physics major. From there, she ventured to SISSA, Trieste in Italy, one of the world's leading institutes in advanced studies, to pursue her PhD under the supervision of none other than Professor Atish Dhabholkar, a name synonymous with groundbreaking work in string theory. During her PhD, Dr. Jain explored index theorems and their fascinating connection with supersymmetric quantum mechanics, a mathematical journey at the heart of high energy physics. After completing her PhD in 2020, she returned to India, joined TIFR Mumbai as a postdoctoral researcher, where she collaborated with Professor Shiraz Minwala on black holes and anti-de Sitter space, a topic which I think ties deeply with string theory and ADS-CFT correspondence. And as of 2024, she is continuing her research as a postdoctoral fellow at the prestigious University of Cambridge. Well, Dr. Jain's insights into the interplay between geometry, supersymmetry, and gravity makes her the perfect voice to guide us through today's conversation on quantum gravity, what we know, what we don't know, and where the quest might lead us next. So, with that, I would heartily welcome Dr. Diksha Jain. Dr. Diksha, a warm welcome, and it is an absolute pleasure to have you here.
Yeah, thanks a lot. Thanks a lot for the wonderful conversation, wonderful introduction, and thanks a lot for inviting me. Uh, I hope you
Absolutely.
guys enjoy it. Yeah.
Yeah, it is a pleasure. We already got a hello coming from hello, sir and madam, somebody called physics, just greeting us. That's wonderful. So I will just tell you quickly, those who are watching today's podcast, that we have got a basic introduction on what we know as quantum gravity that will be lectured by Dr. Diksha Jain. And in between, if you have any questions, please do let us know. And this is something which we are all trying, I mean to say the entire fraternity of physicists are trying to unite two great theories, and we will hear more from Dr. Diksha Jain and what are the avenues, what are the career that we can make up landing up into the famous Cambridge University, where people like Isaac Newton once lectured, right? Dr. Diksha, so I will just put on the screen presentation and you can continue.
Yeah. Thank you. Thanks a lot. As Shanak said, please feel free to interrupt in between and ask questions so that I know how the presentation is going. So, first of all, I'll begin by telling you the motivation of doing what I am doing right now. So, this is the motivation of most of the theoretical physicists right now. So, the motivation comes from understanding the what is the nature, like what are we made up of, what is the nature made up of, what are the things around us is made up of. Once we understand what everything is made up of, how do all these things interact with each other, what happens when I put two, let's say, atoms together, what happens then. So this is a very broad question which even old Greek philosophers like thousands of years ago were motivated by, and this question has been a central question for understanding theoretical physics, for understanding nature. Okay. And the goal of theoretical physics, in some sense, is to find a nice mathematical framework which describes all the particles that we know of and how they interact with each other. So the thing we want to do is to find simplest way in which all these things can fit together. And if I give you an equation, you can tell how two particles can interact with each other. This is the goal of theoretical physics. And then once you find out such mathematical framework, this mathematical framework should be able to predict something for you, should be able to tell, okay, if you instead of doing one, instead of putting two electrons together, if you put one electron and one proton together, what next will happen? And these are the predictions we are motivated by. And sometimes, so the field of theoretical physics goes hand in hand with experiments. So sometimes experimental physicists find some unusual behavior, and then a goal of theoretical physicists is to trying to explain how this unusual behavior can fit into the mathematical framework. Or it works other way around also, that once we find a mathematical framework, we give predictions that, okay, if this theory is true, then this tells us that these particles should be produced. And then the experimental physicist goes to the lab and checks whether those predictions are true or not. So this is the broad motivation of doing physics or doing theoretical physics. And this is the thing which I was motivated by to go into this field. Okay, so let's try to see how do we check what we are made up of. For example, if we go deeper and deeper, if we look at smaller and smaller scales, we find more and more structure. For example, us human beings, we are made up of cells. This you have learned in your school. And each cell is made up of atoms in itself. Okay, even non-living things are made up of atoms. And now, uh, uh, if you have atoms, if you look even inside it, at some point you will think, oh, maybe atom is the basic constituent. It is like the brick, and with that brick you make cells, and then with that cell you can make the full house. That is humans. But that's not the case. If you break the atom, you find that there is structure inside it. The atom itself is made up of electrons, protons, neutrons. So it's itself made up of smaller particles. And then, if you further break these smaller particles, you see that even the protons themselves are made up of something called quarks. How do you find these things? This is very simple. Like experimentally, what you do is you basically bombard particles at very high energy. If you collide two things at very high energy, they will break. And once things break, you will know what are the smaller things they are made up of. And this is what you do. This is what the experiment in CERN, which is Large Hadron Collider, does. And using multiple of those experiments, now we know a list of fundamental particles which have been discovered by CERN. And we want to now understand whether from this list of particles, how they interact with each other. Now, you may ask, okay, how do we know that this list is the full list? In the sense that if we look at more high energy, that is, if I try to break even a quark, maybe it breaks into something else. How do we know that we have found the fundamental particle? The point is, we actually don't know. So at the energy scale CERN is working at, it has found certain list of particles. But maybe if we increase energy, if we bombard particles more fast and all, we'll find some new structure. And this is the goal of theoretical physics, that in the sense, now we'll try to find a framework which will predict, which will tell you what are the all the particles in some sense. And now if experimentally people find there is some other particle which is not included in that framework, then we have to change our theory. So still, so this list is not complete. So that's why I put a question mark. This is still an open field, in the sense that if we have higher and higher energy, maybe we'll find something new.
Right. So this is what I am sorry to interfere, doctor. This is what Dr. Diksha has already set up this stage, that we start with a fundamental question, what we are made up of, and then we try to break up and we reach up to limitations, that there is a scale limitation, energy level limitation of the large LHC, etc., that we are unable to find that. Now, this is wonderful. Thank you, doctor, because you are actually telling something which is basically a kind of a course, a basic fundamental quest, and from there the further complications and the theories would lead up. So thank you very much. I'm listening to it. It's absolutely wonderful. I mean to say, all the viewers must enjoy it. It's a kind of a lecture which has started on a very basic and an easy explanation. Please continue.
Thank you. Okay, so now let's move on to the next question. The next question was, okay, if I give you a list of particles, that these are the fundamental particles, now how do they interact with each other? If I give you an electron, a proton, how will they see, like what will happen if I put two of them together? It turns out that till now, what we have found that there are four types of fundamental forces in universe. Okay, and out of these four, two forces you see every day. One is the gravitational force. Gravitational force is any object which has a mass, any object which is heavy, it attracts another object which is also heavy, and the force with which it attracts is gravitation force. Okay, you might have heard of this famous apple falling on Newton. In Cambridge, apparently there is a apple tree which is said to be the apple tree from which the apple fell.
So it is still, I mean to say, you have seen that.
Yeah, so people told me that this is not the actual tree. This is a seedling from
Okay,
the actual tree which they planted,
okay,
and now it has become a tourist spot in the sense people.
okay, wonderful.
Okay. And the other force is electromagnetism. So electromagnetism is if you have, let's say, two magnets together. If you put north pole and north pole of a magnet together, you'll see that they try to go far away from each other. If you put north pole and south pole together, they try to come to each other. So this force, the force which is between two magnets, for example, is called electromagnetic force. Even electron and proton interact by electromagnetic force. So any charged particle interacts by electromagnetic force. There's another force which is called
Sorry,
strong.
sorry to interfere. Sorry to interfere. There is one person who is telling, Madam, as you did BS from ISER Mohali, I am a 12th grader aiming for IISc or ISERs and want to reach in quantum gravity. Please, can you guide how to get into MIT or Cambridge for MS and PhD? I think that, Dr. Diksha, we can take up this question once we complete this. This would require a little bit of time for you to elaborate, isn't it?
Yeah. So maybe this journey or how to applications and all work, I'll try to
Yes,
address this towards the end.
absolutely. Yes, yes. So physics, please wait until we complete because this is something very seriously doctor is explaining. We will come to your question and definitely we will address that.
Yeah.
Stay tuned. Yeah,
Thank you.
please
Yeah.
continue.
Yeah, so the other third force is called a strong force, which is a force inside the nucleus. It is a force between neutrons and protons, and this is a very strong force in the sense that that's why the nucleus holds it together. Because you could have said that, oh, both protons are positively charged particles. How come uranium, for example, or any other atom have many protons together? But there is this strong nuclear force which is much stronger than the electromagnetic force which binds them together. And then there is another force which is called a weak nuclear force. This is also inside the nucleus. Okay, out of these forces, the first two are the long range forces. You see it far away also, but the last two, the strong and the weak nuclear forces, are very short range forces. And till now, okay, now you can ask, why is there no fifth fundamental force? Experimentally, till now, what we have seen that there are only these four forces. If there were the fifth force, it would have given us some implication on the orbits of planet or on particles in sun, and we have not seen any implication. So that's why this is till now. People, I think, most of theoretical physicists will agree that whatever experimental evidence we have till now, that is consistent with having just four fundamental forces of nature. Okay. Now I have a list of fundamental particles. I have forces with which these particles interact. Now you can ask, can I find a mathematical framework which, if I write down an equation, and that equation will tell me, okay, given two particles, how much force it will how much and in which direction the force will act, and all those things. It turns out that the best framework we know till now is one of is called quantum field theory. So what quantum field theory does is that to every particle it assigns a field. Okay, I'm denoting it by phi. So what is a field? Field is like a function which depends on space and time. And now we write interaction between these fields. And you can now you say field is like a continuum. Where are the particles here? Now you try to quantize those particles. You try to look at the interactions, the fluctuations in this field, and the fluctuations in this field give you particles. Okay, these are basically the excitations around the field which give you particles. So what quantum field theory does is it combines classical fields like a fluid or something, with quantum mechanics. Quantum mechanics is telling you that the excitations around fields are like particles, are quantized. It combines these two things and gives you a framework of quantum field theory. Once you have this thing, you can mathematically write a differential equation in terms of these fields phi, to where you have phi for each of the different particles. So you have many different fields, and you can write differential equations among those fields to describe interactions between those fields and to describe how the forces will act. And this is the
Okay, so
framework.
when you're talking that this classical fields plus quantum mechanics, that means are you referring to the relativistic quantum mechanics or non-relativistic quantum mechanics?
Relativistic. Here I am treating x and t same. Okay,
Same. Okay,
this is a
fine.
very good question. So the point is that usually in quantum mechanics, time turns out to be a nice variable. You treat time and space differently. But in quantum field theory, how do you do it? Is when you write down classical fields, x space and time are at same footing. Then you choose something called a Cauchy slice, which is a slice at a particular time. And on that Cauchy slice, you quantize the field. And from there, you get particles. And that's how quantum field theory works. And now, the third point I made earlier. So I made a few points that what is the motivation of studying physics? The motivation was to find what are the fundamental particles, what are the forces they interact with, then to find a mathematical framework to describe them. But then this mathematical framework should be the simplest framework. It's not like if I give you a equation with 100 variables and I try ask you to solve it, and I say this is the theory of the universe. That is not a nice or simplistic mathematical framework. So physicists always try to find the simplest possible way you can describe a physical system and interactions. And finding the simplest possible way is basically trying to find new and new theories which can incorporate things together. So one such simplification is called is unification of forces. This Maxwell saw in 1800s. For example, if you just see electricity and magnetism, if you just see a current or you see magnets, you would not think that both of them, the underlying theory for both of them is the same. And Maxwell realized this, that if I change current, then it can produce magnetic field. This is a solenoid example you might have heard. Okay, hence electricity and magnetism could be put together into one theory, which is the Maxwell theory of electromagnetism. This is a huge simplification. Before electromagnetism, people used to think electricity is different than a magnetic field and used to describe them with different variables with different mathematical equations. And then what Maxwell did was to combine these two equations into a theory of electromagnetism. This is again something theoretical physicists try to do, which is try to find the simplest framework under which multiple things can be described. So since when electromagnetism was found, this after that the goal has been to unify all four fundamental forces. So the four fundamental forces were gravity, this electromagnetism, strong nuclear force, and weak nuclear force. And by late 1900s, people managed to unify three out of these four fundamental forces. So electromagnetism, strong nuclear force, and weak nuclear force, people managed to unify into what is now called standard model of particle physics. There has been a lot of Nobel Prizes which have gone to people who discovered the standard model of particle physics. And this is a very nice framework in the sense that it gives you a quantum field theory equation which tells you how these particles interact with each other and how all three different forces act on these particles. And it also had a predictive power. Standard model predicted that there should be a particle called Higgs way before Higgs was actually discovered in CERN. So this is how sometimes theory gives you predictions. Usually people used to think that, oh, experiment will find something and then we will try to write down a theory to describe it. But the other way around can also happen. That theory predicts that there should be a Higgs particle, and this was discovered. If we didn't discover Higgs, we might not have said that standard model is a correct theory. Now, the question remains that what about gravity? All these forces, three forces were unified, but gravity is still not unified in the standard model of particle physics. So, this is the thing which I am working on right now, which most of the people in quantum gravity community are working on. So there are a lot of difficulties which arise when you try to put gravity together with other forces of nature. One of the thing is called background dependence. So as I told you, the fields in quantum field theory were dependent on x and t, space and time. What is gravity? Gravity, Einstein's theory of general relativity, tells you how space and time change due to the presence of mass. So space and time themselves should be dynamical variables, should change. But in standard model, space and time, you fix the space and time, you fix a particular space time, and then you have fields on top of it. So making the space and time change is a difficult problem to do. It is called background dependence of quantum gravity, and we want to make it background independent. Uh, Also, there is something called non-renormalizability. This is a difficult thing to explain without going into mathematical details, but I can tell you that uh, in quantum field theory, usually one runs into a lot of infinities while solving mathematical problems, but we know a way how to understand them. With in gravity, you can't do that. There are issues with something called that gravity is not renormalizable. Then there is something called the black hole information paradox, which I'll come to in next slide, which one has to explain if we have a theory of quantum gravity.
Okay, here I have a question, Doctor.
Yeah.
The Klein Gordon equation was perhaps the first equation which tried to unite quantum mechanics and relativity in a kind of a relativistic framework. So, what was the limitation of the Klein Gordon equation? If you can just explain us.
So Klein Gordon equation, there also you need a background metric. So Klein Gordon equation is box minus m square. Box is dependent on your G mu, the metric. But now the metric itself is dynamical. Einstein relativity tells you the metric itself changes. And Klein Gordon equation does not take that into account. It does not change the metric. Given a metric, it tells you how fields will behave in presence of this metric. But now you want to change the metric itself. And when you try to do it naively, when you try to quantize it, when you try to do it naively, you run into these infinities and all these other problems. Yeah. Okay. Now you may ask, what is the need of quantum gravity? Is it because we wanted to simplify nature, we wanted to simplify our mathematical framework and wanted to unite, combine all forces of nature? That's why we needed quantum gravity. Is this enough motivation to study quantum gravity? We might say, oh, there is a theory which is standard model which describes three forces. There is another theory which is general relativity which describes the fourth force, and we are done with it. Why do we need to combine these? It turns out that in physical situation, there are situations where you need effects of both together. And one such physical situation is a black hole. This is a picture of the black hole which was discovered a few years ago, and there was a Nobel Prize on it. On the person who clicked the photo also got the Nobel Prize. The person who predicted that there should be black holes also got the Nobel Prize. So black holes exist in nature. This we know by now. Okay, Einstein predicted that they should exist 100 years ago, but we now have seen them. So they exist. And black holes, what are black holes? Black hole is a object which is so heavy that so anything which is more heavy has more gravitational force. So and black hole is so heavy that the gravitational force is too high that any particle which tries to escape it cannot escape it, because it pulls it towards the center, so with such a big force. And that's why even light cannot escape. So the thing that you see, which is the light around it, is the black hole is inside it. So the light around it is basically on the horizon, and anything which is a bit inside that part cannot escape. Okay. And now in black holes, what can happen? We know, so Penrose, who got the Nobel Prize for theoretical understanding of black holes, Penrose found that the when you write down metric of black hole, you find that there is a singularity. So singularity is a place where both quantum effects, because it's a very small space, and gravity, because black hole has a huge gravitational field, become important. So in black holes, and this the same thing happens during Big Bang. So when our universe began, then also universe was small and gravitational force were huge. That's why there are in nature there are phenomena where both quantum mechanics and gravity are important. That's why we need to understand how, when these two forces are combined, how it works. When the That's why we need quantum gravity. It's not just for mathematical simplification, it's also to explain physical effects where both gravity and quantum mechanics are important. And black holes have a very nice property. This is one of the most beautiful formula which I find in physics, is the
This
entropy
is
of the.
the okay. Is this the Hawking radiation formula?
This is the Bekenstein Hawking entropy formula.
Bekenstein Hawking, right?
Yeah, yeah.
Okay.
And Hawking was also in the same department where I am. So Hawking discovered this formula while he was here, I think. And so this formula is very interesting. So this tells you what is the entropy of a black hole. So as you know, if you have learned thermodynamics, any system, any physical system, you can assign entropy to that physical system depending on how many degrees of freedom that system has. Now, this formula is interesting because the black hole Hawking basically told us black hole is like any other thermodynamic system. It has entropy. B, the entropy is proportional to area of the black hole. Usually, if you have a system, the entropy you will think is proportional to its volume, because more the volume, you can put more stuff in and hence increase the entropy. But for black holes, the entropy is proportional to its area of the horizon, not its volume, which is a strange feature which very few physical systems have. Other thing is that this formula has so many fundamental constant. It has h bar, which tells you there is a quantum mechanical effect. It has g Newton, which tells you it is a general relativity effect. So this combines gravity and quantum mechanics. There is kb, Boltzmann constant, which is basically there is a thermodynamics. So this formula combines thermodynamics, gravity, quantum mechanics, which
Right.
is
And
not
c to the power 3 is the speed of light
speed
in
of
three
light. So it's a
dimensions.
relativistic formula. Yeah. Uh, so which is, I don't think you would have seen any other formula which has all so many forces of nature together and so many different fields of physics together in one formula. So this is one place where you see that this formula, if you have to derive from some microscopic physics, you need to understand the effect of gravity and quantum mechanics together, because both gravitational constant and h bar, which is telling you about quantum mechanics, comes here. So we know black holes exist. If we want to understand everything in nature, we should also try to understand black holes. And if we want to try to understand black holes, there is no way to understand them without combining quantum mechanics and gravity. Hence, quantum gravity is needed. Okay. And there are various frameworks which have been developed over last 50, 60 years to try to explain how quantum mechanics and gravity can combine. These are names of few. I work in string theory, so I'll just talk about that. Other frameworks have some uh, uh, good things as well as some bad things. And I think it's just what you start working on, you start liking that framework more. But I will tell you the motivation why I work on string theory, not on any of other frameworks. So, string theory is what is string theory? String theory basic idea is, instead of considering particles as point-like thing, you consider particles as strings, as an extended object, where the length of the string is very small, and hence when you measure it in CERN, you see them as a particle. Like if you
Okay.
have,
I've got a question just for my curiosity. That say, for example, whether it is observational work, etc. When I was hearing the lectures of Leonard Susskind, considered to be the father of string theory, there also one of his informal lecture he was explaining that particles are considered to be as strings, tiny frame vibrating. Now, doctor, is there a motivation or a reason that suddenly from a point like particles, why we are thinking as a string, not as a cube or anything else? I mean,
Yeah.
is there a, yeah.
Okay, so the history is very interesting. Actually, the history that considering particle as strings came from trying to describe quantum QCD, came from trying to describe quarks. So Italian physicist Veneziano and all, there were some experiments with scattering of quarks, which they were not able to reproduce the answers of, and then they thought, oh, instead of thinking these as particles, let's try to think them as strings. Okay, so initial motivation came from there. That time there was no string theory that helped explaining some other part. But then string theory, now you can ask, why just a string? Why not a plane? Why not a 3D thing? Actually, those type of objects also exist. There are something called D branes, which are a part of string theory, and the excitations around those D branes you can again quantize, and D brane can have any dimension, and then there are certain consistency conditions that comes. So a good thing about string theory is that there are a lot of mathematical constraints that comes from theory, and turns out that if you try to like do anything outside which violates those mathematical constraints, you will everything will fall down. And so how many dimensions are allowed, how many branes are allowed, given a brane, how it can couple to other fields, all these things are dictated by the mathematics. So you can't just put like a two-dimensional object and say that it produces a field which is a higher dimensional field. No. So there is a mathematical consistency that comes about it. And those objects are included in string theory. These are higher dimensional objects called branes, D branes. Okay. Uh, and okay, so the good thing, the achievements of string theory have been the following. It has managed to combine all four fundamental forces. So it has combined, it's called, we call it a UV completion of gravity. So it has managed, so in string theory, the mathematical answer, the framework you get is you have all four forces of nature. So it has managed to combine all four forces of nature. It has given us a new perspective for gravity, which is called holography, which I'll come to in next slide. And the most important thing, I think this was the reason I personally chose to work in string theory, apart not any other frameworks of gravity, was because it gave us an explanation of black hole entropy. The point I told you that there was this formula for black hole entropy, and it told that black hole entropy is proportional to the area of its horizon. And now, if you have done thermodynamics, you know that any object which has entropy you should be able to understand that as log of degree of freedom, where degree of freedom are the things inside that object. And in string theory, by actually counting microscopic degrees of freedom, you are able to reproduce this formula for the entropy of black hole. And people found corrections to this formula. So the formula that I showed was considering that general relativity is the theory in which you are considering black holes. If instead of general relativity there were some higher order terms in the Lagrangian, if it was some other theory in which there were black holes, there will be corrections to this formula, and string theory can reproduce those corrections as well, which is a very big thing. There are certain corrections which are universal, which are called log corrections. I don't think any other framework of quantum gravity has been able to reproduce those log corrections by some microscopic counting of degrees of freedom.
So that
So that,
means the biggest triumph of string theory is the correction factors, and we have been able to unite all those four forces. And even the black hole and others, you are telling that there are correction factors, which is bringing the theory in a very nice and a proper manner.
yeah. And then these correction factors you can compute from the gravity side and from the microscopic counting, and you are able to reproduce it. The the thing which I should say here is this all these computations have been done for supersymmetric black holes mostly. So the black holes which preserve some supersymmetry. So for Schwarzschild type black holes or the black holes in our universe, maybe the calculations are not that precise because they have been done for supersymmetric black holes. But even if you have done these calculations for a particular type of black holes, it shows a what do you say, proof of concept in some sense. The point is, for other black holes, counting for if supersymmetry is not preserved, counting degrees of freedom is a very difficult problem. This is the problem my supervisor Atish Dabolkar. So this counting black hole microstate, these states are called the Dabolkar-Harvey states. Basically, he worked on during his PhD. And this is a yeah. Now I will come to holography. So sorry, I'm taking so long.
No, that's fine. That's fine. We are all enjoying. Before coming to this, if you can just explain us the concept. We in museum, etc., we have seen what is a hologram, but holographic principle, how did it came and why it was a little bit necessary? If you can just give a
Yeah,
little bit of background. Yeah.
yeah. So I can give you two reasons. Like these reasons, I think people came about. These reasons came about after maybe discovery of holography. I don't know. Maybe before, I don't know the history. One reason why gravity should be holographic. So what holography means is that you have a system, let's say, and then that system can be described by degrees of freedom living on its edge only. You don't have to go inside the system to understand that system. Okay, this is like holography. Hologram is like that, no? So what principle of holography says you that a theory which has quantum gravity in some region, that quantum gravity theory can be described by some other theory which lives on the boundary of that region. Okay, now, why do you expect this to work? One reason was the black hole entropy. As I told you, black hole entropy is proportional to uh, area of the horizon, not its volume. So the black hole entropy depended just on the degrees of freedom on the horizon, not inside what is inside. So this tells you that something special has to happen so that the entropy is dependent on area, not on volume. Because entropy in thermodynamics, you might have heard it's an extensive quantity, it depends on volumes. But for black holes, it depended on area. So the objects which have strong gravitational field, somehow the number of things you can put in it is proportional to its area, not its volume. So it tells you that there should be holography. There's another reason. If you try to just take Einstein-Hilbert action, if you try to take Einstein gravity, that is a Lagrangian, you try to write down the Hamiltonian corresponding to it, you will see that the Hamiltonian of that system is just a boundary term. There is no bulk term in the Hamiltonian. So that also tells you that the dynamics should be described by something just living on the boundary. These were the two motivations why you think that holography should work.
Okay, so both of these things are saying something within the boundary, and that is why it came across. Okay,
Yeah.
wonderful, amazing. Thank
Yeah.
you. I will just put on the slide. Yeah.
Yeah. In string theory, the principle of holography was actually derived in the sense that you took a system of d branes and then you looked at it in certain regime. There are two different ways to look at the same system, and one way gave you a quantum gravity theory inside the bulk, other way gave you a field theory living on the boundary. Because the system you started with was the same system, it tells you that those two theories should be equal. It's basically you try to say A is equals to B and you also saw B is equals to C, it tells you A and C should be equal. So this in string theory, actually ADS-CFT correspondence is something which we have derived. For other things, we have not derived it. Okay. So for ADS-CFT, what it tells you that if you have a gravity in a theory which lives in anti-de Sitter space. So for our universe, for example, is a de Sitter space, which is an expanding universe. Anti-de Sitter space is a universe with a negative cosmological constant. We have a positive cosmological constant. So if you have a quantum gravity theory in that space, then that theory can be described in terms of a theory which is not quantum gravity, which is just normal quantum field theory, which doesn't have gravity in it, which lives on the boundary of the space-time. And that theory is a conformal field theory that has more symmetries. Conformal means it has more symmetries. Okay. and this principle has been tested to death. Okay, so the current one of my current projects which I was working in was also basically we have some black holes in the entity sitter space, and having a black hole in the entity sitter space tells you what should be there in field theory, in the conformal field theory, and you can actually reproduce the entropy of the black hole from doing a calculation just in the field theory. You can actually, you don't have to do a gravity calculation, you can do a quantum field theory calculation and reproduce black hole entropy with a black hole present in the bulk. And there are a lot of achievements of this principle. Okay, of course there are a lot of open problems, that's why there are so many physicists still working in this field. One of the major open problem is how to extend the principle of holography beyond entity sitter space. So the reason why holography should exist, the reasons I gave you, both black hole entropy and the Hamiltonian being a boundary term, this is true for any space-time, for flat space, for de Sitter space. But we have been able to derive holography starting from basic principles only in entity sitter space. We have not been able to derive it in other space-time. Our universe is a de Sitter space, which is an expanding universe. So if we want to apply principle of holography to our universe, we should be able to extend this holography principle. And there are a lot of problems in trying to extend this beyond ADS space. Another thing is that we understand the black hole entropy quite well, I feel, but we still don't understand the singularity. So singularity is this singularity we can't access, in the sense that if a person goes inside the black hole, only that person will see singularity, but that person can't come out to tell you what happened there. Okay, but
Just one question. In this case, when you're saying that understanding black hole singularity and Big Bang singularity, I had a podcast earlier with another person from Brazil. And now this naked singularity, which is not covered by event horizon, that means is this part of quantum gravity not considering singularity? It is considering classical singularity, that is an event horizon, and then beyond there is a
yeah,
singularity.
yeah, yeah. Yeah, I
Okay.
think there
Okay.
are a lot of theorems saying that there should be no naked singularities. This is called cosmic censorship. There are ways uh, mm, to go around that theorem, but I think most of the physicists believe that there is cosmic censorship. Like Penrose, I think Penrose gave it. Yeah, somebody made that conjecture that whenever there is a physical singularity, it has to be surrounded by a horizon. That's why you can't directly go and do measurement at singularity. But the point is, singularity is a place where the space time is very small, so quantum effects are important, and gravitational field is very strong. So gravity is also important. So singularity is if we understand quantum gravity better, singularity is something which we should understand. For example, in holography, a lot of people are trying to understand the implication of singularity on the quantum field theory side. And there have been some papers recently trying to understand it. Another thing is how to recover standard models from string theory. This is a big criticism of string theory. The big criticism being, I told you string theory combines all four forces, but after string theory lives in 10 dimension. Okay, why 10 dimensions? It's another presentation to tell you why 10 dimensions. But now
Actually, I got a question today from the subscriber asking that, sir, why do we have so many dimensions in string theory? I thought that hopefully Dr. Diksha will answer in today's
okay.
podcast.
The point is we have we have a lot of dimensions in string theory. It comes from mathematical framework only, in the sense that when you try to quantize the strings, you see that the commutation relations make sense only if you put them in higher dimensions. Otherwise, you get some things which are negative, which you don't want to. But now you can say, and there are like a lot of different checks and tests, in the sense there is something called anomaly. Theory of quantum gravity should not have anomaly. Anomaly is that there is a symmetry at classical level, at quantum level that symmetry is broken, but gravitational symmetry should not get broken at quantum level. So if you try to make sure that there is no anomaly, that the system does not break uh, gravitational symmetry, diffeomorphism symmetry at quantum level, you will see that the only way you can make it consistent is to take the dimension to be 10. Okay. And now you can ask, but we see only 4 dimensions. Okay, when I say 10, I include time in it. Okay, so we have 3 length, breadth, and height, 3 spatial dimensions, and 1 time. We only see 4 dimensions. Where are the other 6? The point is that the other 6 dimensions are very small, and hence we can't see them. It's basically like if you have a paper, you will say that it's a 2-dimensional object, but it also has some height. It's very small. So if for other dimensions are very small, you can't see them basically. And the
I mean to
scale,
say it is just like this Kaluza-Klein theory, a
yeah,
pipe which has got a thing, and then you're
yeah,
okay. So Kaluza-Klein is also harping on this fact that there should be extra dimensions.
yeah, yeah, yeah. As you're saying, Kaluza-Klein combines actually gravity and electromagnetism together. If you consider 5D, which is a very nice. And now, so you have 10 dimensions. So the other 6 dimensions are very small. That's why you can't see them. But now, if I have a theory in 10 dimension, there are multiple ways to come to 4 dimensions, and this is called string landscape. And if you allow all possible things, you get like 10 to the power 6 number of theories. And out of those 10 to the power 6 theories, we live in standard model, no, which has been tested. So we know with what theory we live in. Okay. How do one reconcile this fact that starting from that 10-dimensional theory, you land on this unique theory which has been tested? You get a lot of theories. Standard model can also be a part of that, a lot of theories, but you get so many theories. How do you rule out other theories? How do you say what is wrong with other theories, or why our universe we live in this particular point of this many compactifications possible? This is called landscape problem, and there are a lot of people trying to work on it, and they have found a consistency condition set of rules which should tell you what are the allowed 4-dimensional theories, but still we have not been able to single out standard model. Yeah, that's it. Okay, so these were the all the slides I had prepared. I can.
Okay, fine, fine. So I can put off the slides and go directly to the questions. This is amazing. I would first like to thank you. We got a complete, I would say, what a lecture, starting from the what we need, and then we go back to the. Okay, one question before I take the questions. The contribution of Professor Leonard Susskind in terms of string theory, what is his actual contribution? Why is he so famous, other than being a great teacher?
Yeah, so he has made a lot of contributions. So Leonard Susskind is a kind of person who gives groundbreaking ideas, and then from those ideas, people work out calculations and see, oh, his idea was actually correct. Okay, so for example, one of his recent ideas, which a lot of people are working on, is to interpret black hole entropy as entropy coming from entanglement, as an entanglement entropy between the things outside black hole and inside black hole. And he just gave that as an idea, but it turns out to be very reliant idea. It has been tested mathematically, and it gave a new connection. Actually, it gave a connection between computer science and quantum field theory and gravities. And then there are a lot of, so he has been in this field for a long time. He has given something called giant gravitons. There are so many contributions that he has given, even understanding black hole entropy. uh, I personally think he's kind of a person who gives an idea which naively, if you look at it, you will be like, why it should be true, and it turns out that it's true. So he has a very great intuition. Yeah.
Great. Yeah. I will just take up quickly the questions. Okay. The first question is that, ma'am, as you did BS from ISER Mohali, I'm a 12th grader aiming from ISC ISER and want to research in quantum gravity. Please, can you give a guideline to how to get in MIT or Cambridge for MS and PhD?
Yeah. So usually what happens is that so I did my thing in ISER. ISER has a 5-year program, as you might know. The first 2 year you study everything: physics, chemistry, math, biology. Now in some ISERs it's 1 year, in some ISERs it's 2 years, and then in 5th year you do a master's project. So when you are doing your project, so there are multiple things you can do in between. In the sense that there are summer projects which people do. For example, I did a summer project in Germany under DARD fellowship. And I worked in a quantum computation lab during that summer project. So one thing, once you go to these institutes, ISERs, IISc, your chances of getting selected for good summer programs also increases because people know these institutes. Once you go to these summer programs, you actually make connections. You get to know different professors, you get to know whom you can apply to, whom you cannot apply to, all those things. And then in the last year, you can give exams, which is a GRE exam to apply for PhD in US. Then you can also apply because you have already done masters in ISA. So there are two things. If you want to come to Cambridge, mostly people do another masters because Cambridge has something called a Part 3 program, which is what people come here for. And then after doing that Part 3 program, there's an exam, and then if you clear that exam, you get selected into the PhD program here. But instead of doing masters again, you can actually directly apply for PhD programs as well. But usually that applications you start during your last year in MS. And when you are in the last year, since you have done so much of summer project experience, so you have good CV, because when you apply, people look at your CV, what things you have done, and people look at the recommendation letters. You will need letters from like 2 or 3 scientists, and if you have done summer projects, those people can write letters for you. And then there is a Part 3 program of Cambridge which you can apply to. There is a program in Perimeter which you can apply to. There is another, and then there are PhD programs all over the world which you can apply to. And there are these exams called GRE, and then there is uh, sometimes you have to give TOEFL or IELTS for English to come to certain countries.
Okay,
Uh,
okay. So, as Cambridge is a very expensive place, I mean to say, how do you manage the food and the staying? Do they provide a sufficient allowance from the university as a
Yeah. So
postdoc fellow?
so as a postdoc fellow, I'm given a good salary. And the housing which I live in is, as you said, Cambridge is very expensive. So the housing is a subsidized housing. So given the, like, these are very nice houses which we live in, but we pay price which is still a lot, but less compared to the market price. Yeah. But usually, but this is a good point. The people who come here for Part 3 program, only few of them get scholarships. So there are two levels of competitions. One is to get into the Part 3 program, another is to get the scholarship. And I know some people who have come here, but they took a loan in India and then they came here. But this only master's programs are there without scholarships. But once you join a PhD, you will get scholarships, and you will get money to, yeah. And in postdocs and all, you can actually save money as well. So it's a good salary usually.
Okay. Coming to the next question, David Dexter is telling, what is the highest package and job opportunity after completing MS and PhD from good university?
Okay, so it depends on whether you want to stay in academia or you want to go outside academia. If you want to go outside academia, for example, for the theoretical physicist, for the person like me, the opportunities are to go to finance, because uh, because what finance people need is like mathematical, knowing how to solve differential equations. That's what basically they need. So you can go to finance, you can go to uh, there's a startup called Anthropic, which is in AI. Basically, you can go in AI, you can go in machine learning. But for all those things, you need to acquire some extra skills apart from your PhD. For example, during my PhD, I did some programming and all. But if I wanted to go into machine learning, I needed to do more programming. I should have learned more programming to give that interview. So if you want to go outside academia, you can go to actually very high paying jobs. I have some friends who have left academia and are earning a lot. But if you want to stay in academia, then you don't get that much money. In academia, usually, yeah. So for example, in India, if you become a assistant professor, as an assistant professor, you get like 1 lakh, or a bit more than 1 lakh per month, and then maybe 1.5 lakh, and then you have some extra advantages on top of it because it's a government job, so you get TA, DA, housing, all those things. But of course, that money is less as compared to what you will get in a startup company, let's say. But it depends on your interest, whether you want to pursue academia or not.
Or not, right? Okay. Raghav Manchanda has got a question. Ma'am, how graviton particle mediates gravity?
Okay, yeah. So this thing I didn't go through in the talk, but usually, as Raghav is saying, usually all the forces you can understand that the forces are mediated. So if there is an electron, there is another electron. They will repel each other. We know because of electromagnetic force. But you can understand that this force acts by exchange of some particle, and this particle for electromagnetic force is a photon. Okay, for gravitational force similarly, the particles which will get exchanged when some forces are acted is called graviton. In other words, graviton, you can think of graviton as taking the gravitational field and you quantize the fluctuations on top of that gravitational field. Those quantized particles are the gravitons. And the good thing about long range forces, any force which is a long range force, for example electromagnetism or gravity, the corresponding particles are massless particles. Okay, photon is a massless particle, graviton is a massless particle. For short range forces, they need not be massless particles.
Okay, we have got a very interesting question. Ma'am, quantum mechanics is based on probabilistic and GR is based on determinism. So at singularity, when these were united, does it make sense?
Yeah, okay. So this is something alluded to basically in black hole information paradox, which I didn't go into. When we say quantum mechanics is probabilistic, it doesn't mean that it is not deterministic. Quantum mechanics is fully deterministic in the sense that if I tell you that this is my wave function, I can tell at time t, I can tell you what will be the wave function at time t plus delta t. I can exactly tell you what will be the state. It's e power IHT. So it basically tells you that the time evolution operator is a unitary operator. Okay, that is, so in some other way the probability is conserved. Okay, so this is called unitarity, and quantum mechanics is unitary. But when there is a black hole information paradox, what people say is that okay, as I was saying, that if there is a black hole, something which goes inside doesn't come outside, you can now ask, oh, if I have if I have a particle, it goes inside the black hole, and it will anything that comes out of the black hole is just this Hawking radiation that does not have information of what went inside. So how is this deterministic? I throw an electron. I know what is the charge of this particle. I know everything. That went inside the black hole. But when it came out just as a radiation at some temperature. It doesn't have information about the details of what particles were inside. And this is called black hole information paradox. And this is a big open problem in theoretical physics. There are some resolutions which people know in holography, because in holography we know that dual field theory is unitary and hence information is not lost. But purely from the gravitational side, we still don't understand, because it seems that the information might have been lost. There are, okay, I should not say we still don't understand. We understand, we have recovered page curve and all, but that is in specific context. Yeah.
Right. Got the next question, different something. Teachers, if the mass of the sun gradually decreases, then what happens to the orbit of Earth? Will it remain elliptical?
Oh, okay. Yeah, I think elliptic comes from the fact that from the directions basically, the mass decreasing will change the strength, so will change the size of the ellipse. But I thought it will remain ellipse because it is elliptical, because it's a three body problem in the sense that there are other planets also which are pulling Earth. The size of this ellipse will depend on the mass of the, for example, sun, and the mass of other planets around. So the size of the ellipse, its major and minor axis might change, but I would imagine, like naively, that it will remain ellipse. Yeah.
Absolutely. Okay. Next question from Jason. Newton's universal gravitational equation, the constant G, why is it there? Why does it have the physical dimensions and value that it does?
For example, any force has some physical constant describing it, and the value of this physical constant is fixed by experiment. For example, if you have electromagnetic force, two electrons when they interact with each other, there's this factor 1/4 pi epsilon naught, which is called permittivity. I think it's called permittivity. That factor, which is on the force, because what theory tells you is that these two things should attract each other, and the attraction should be proportional to what is the charge, what is the mass. Okay, but it does not tell you how much proportional. So the factor in front is fixed in some sense by experiment. But the good thing is, once this factor is fixed in one experiment, it should remain same for other experiments as well. For example, if I fix the value of G Newton by looking at the force, uh, one apple applies on another apple. Sorry, by looking at the force sun applies on Earth, uh, and I measure that force somehow, and then I fix the G Newton. But then when I will compute the force applied between Moon and Earth also, I have to use the same G Newton because that is a constant. Okay. So these fundamental constants, for example, Boltzmann constant, which comes in thermodynamics, Newton's constant, h bar, these are in some sense fixed by experiment. These are, yeah.
Right. Okay, Raghav Manchanda is asking, ma'am, what is Hoyle-Nerlicher theory of gravity?
Oh, I don't
I
know.
think, yeah, we can skip this question.
Yeah,
Okay. Next
really
question
sorry.
coming up. No, not a problem. Ma'am, can you explain M theory, ADS-CFT correspondence and the work of Edward Witten?
Yeah, okay. So ADS-CFT, I already told you, the holographic principle, it tells you basically a theory of gravity in anti-de Sitter space is dual to a conformal field theory. Conformal field theory is a quantum field theory with some extra symmetries. There's a scaling symmetry in it. Okay. What is M theory? M theory is the following. So string theory, I was saying that it is valid in 10 dimensions, and it turns out there are 5 types of string theories you can have in 10 dimensions. What I mean by types of string theory is basically telling you what okay, yeah, I have to go to without saying something mathematical. Okay, there are 5 types of string theories. This, okay, you agree, depending on number of supersymmetries and all. But then M theory is a framework which combines all of these types. So you go to one more dimension and you are able to see that 2 of these string theories came from the same theory actually, depending on which limit you took. So
I think, Dr. Diksha, Ashok Sen's contribution was exactly this, that all of these theories actually come from one single theory.
yeah. So Ashok actually made a lot of progress in this black hole, counting black hole microstates, like a lot of progress. He has amazing papers on this log corrections, and then as you are saying, on this M theory as well. So basically, M theory is a theory which lives in one higher dimension, so in 11 dimensions, but it combines all the string theories together. This is like, again, it again came because of this motivation of physicists to combine everything together into one theory. Okay. And the contributions of Edward Witten. So Edward Witten has done a lot in our field. He is the only physicist who got a Fields Medal. So he has done not only a lot in our field but also in mathematics. He has basically given. So there is something called Witten index, which is basically telling you how do you count supersymmetric states. Okay, in a theory, I told you, to compute black hole entropy, you need to count. In string theory, people have been able to count the number of states, the number of degrees of freedom, and put it equal to the entropy. And this counting problem was defined by Witten in a simpler context, and then this counting problem has a lot of this is what I worked on during my PhD also. It has a lot of overlap with something called index theorems in mathematics, and using them, Witten actually proved an index theorem, which mathematicians proved it in like 20 pages, and using some quantum mechanics thing, using a physics thing, Witten proved it in like half a page, something. So yeah, this is like one contribution I'm talking about because I worked on it, but he has given like numerous contributions.
Many contributions. Okay, quickly taking up a lot of the questions, so we will just rush up. Ma'am, can you recommend books which tells about history of string theory except Elegant Universe?
Oh, so good question. History of string theory. There is a Stephen Hawking book, no, Time, Era of Time or something. I don't know if it talks about history of string theory, but
We can
yeah,
we
I
can
don't.
find it later. I can
Yeah,
just
yeah. I'm
email
not
or
a good person to ask. Sorry.
Okay. The same person is asking, ma'am, can string theory can tell about what was before Big Bang?
No, actually not. So the problem, as I told you, that we don't still understand black hole singularity. Similarly, we still don't understand Big Bang singularity. So uh, the point is, from the observations, what we can see is that there is a point after which inflation happened, and after that we can measure the fields, the primordial fluctuations. This is what cosmological data measures. But before the inflation, when the universe was very small, what happened, we don't know. The natural thing we do is to just extend this thing, that the universe was very small, it expanded, but before it was very small, it was smaller and smaller and smaller. And if you just keep on extended this, you will think that there is a singularity, in the sense that there will be a point when the universe is extremely small and the curvature is very high, which is the Big Bang singularity. But whether this extension is also correct or not, it's we don't know, because the only thing which we can measure is after inflation. Okay. And what happens at the singularity, we don't know for black hole, for Big Bang, because those singularities are very similar in nature. We don't know. And once we understand quantum gravity better, if we understand, for example, holography in de Sitter space in expanding universe, we can maybe understand the singularity, because the universe is expanding. If there is another framework which is telling you that there is a quantum field theory which describe gravity in de Sitter space, then maybe we can understand. But we don't have it right now.
Okay. Siddheswar Mukhopadhyay is asking, ma'am, what is the idea of large extra dimension posed by Nima Arkani Hemd? How is it different from compactification?
Nima's idea, large extra dimension. Oh no, so there is this large D expansion which people do because it simplifies some equations in fluid dynamics and in black holes. I don't know if you're talking about that large D, or uh, the thing I know is that sometimes some of the formulas of there is a correspondence between black holes and fluid dynamics, and those correspondences become easier to solve if you work in higher and higher dimensions. So instead of working in 4 dimensions, if you work in large dimensions, you can. But I don't know if whether Nima's idea was this or some other thing. Nima right now is working on amplitude, so I don't know if.
Okay, okay. Pre-Western Leonard Susskind's GR's class on YouTube is top notch. Yes,
Yeah.
obviously. His understanding physics for students is the best university. Thank you for that. Okay. Uh, okay. Another question, ma'am. What are the major breakthroughs in string theory in 21st century?
Yeah, so 21st century meaning after 2000 something, no? Because ADS-CFT came in 98. So I was going to say ADS-CFT, but okay, you are saying uh, after ADS-CFT. So one of the major breakthrough is ADS-CFT, but now also another breakthrough is I would say in some sense is entanglement entropy. It's trying to understand uh, entropy of the black hole as an entanglement between two states, and you are able to actually reproduce it. People are able to reproduce page curve using this thing, and hence able to solve the black hole information paradox, thinking of the black hole entropy as a entanglement entropy. So I would say that that is like one of the major breakthroughs uh, of ideas, like a new idea which came. Then there were some old ideas which got revived. There was something called bootstrap of S matrix, which was there in 60s, which got revived. Now with better techniques, people are able to actually predict some of the things which should happen in CERN, and a lot. Yeah, so and also Cyberg-Witten theories. I think they came after. So there has been a lot of progress in supersymmetric
Right,
theories, which is called
right, okay,
Cyberg-Witten duality. And all.
right. Seema Datta has got a question. Why being massless particle is a good thing? Can you explain?
This is a very good question. So there are two or three things. One is when something is zero, exactly zero, it means there is some symmetry protecting that thing. Otherwise, it could have been a little bit more, no? So whenever there are massless particles present, it tells you that your theory will have some symmetry. Okay. And any which is a good thing, because symmetries people love because it simplifies equations. And if there is a force which is mediated by a massless particle, for example a photon or a graviton, that force will be a long range force. Okay, so that force will remain till infinity. So for example, The strength of the force can decrease. So if Earth and Sun were further apart, the strength will decrease, but the force will still remain. Okay. And another thing about massless particles is, as I was saying, it tells you about symmetries. For example, if there is a symmetry in the system, which is broken by some dynamics, if that produces something called Goldstone bosons, which are massless particles. And Higgs, the prediction of Higgs also came by thinking of breaking of electroweak symmetry, which is a very nice mechanism that happens. So yeah, massless particles are important, and they are usually related to symmetries. That's why.
Okay. Akash is asking, did my MSc from IITD and now I am into MTech in aerospace engineering from IITK. I plan to do PhD from IITB on gravitational waves. Kindly give me some suggestions for a postdoc in reputed institutes.
Yeah, so when you do your PhD, actually, for postdocs, it also depends on what you are exactly working on during your PhD, because postdocs become very specific in the sense that people want to hire people who have worked on who have similar interests, because gravitational waves is a big field, no? So if you are doing like a particular sub thing in the gravitational waves, then the people who are interested in that particular things can be. So there is this Max Planck Institute in Potsdam, which has a big gravitational wave group. Even TIFR in India has a good TIFR as well as ICTS in India has good gravitational wave group, because there's LIGO in India, so that's why there are good uh, groups. So when you do your PhD, you will be reading papers of a lot of people. No? There is a person in Edinburgh who is very good and works on gravitational wave. But those people you will get to know once you read papers in PhD, because you will be working in a very narrow field. So the postdoc institutes will depend on where those people in that narrow field are working on. Yeah.
Right. Abhijit Kumar is asking, ma'am, when we analyze the ADS CFT model, then it is a figure comes out to be the same as elliptic function.
Sorry, which
I also
elliptic?
don't understand this
Yeah,
question.
there is
I
there,
think
there are yeah,
huh.
there are these.
Actually,
Yeah,
I
sorry.
think he's talking of the elliptic function, the modular function, which is
Okay.
referred to.
Yeah. So those, okay. So in ADS-CFT, when you count number of states, for example, in conformal field theory. So in conformal field theory, if you write down the partition function in conformal field theory, because of the symmetries of the conformal field theory in 2 dimensions, for example, that partition function is a modular function. And similarly, elliptic functions also come when you have a non-compact target space and all. So these functions appear when you compute partition function of the theory. And modular function specifically appears for partition function of a 2 dimensional conformal field theory, not higher dimensions. Okay. Uh, and why partition functions are important is because ADS-CFT correspondence tells you that the partition function of the theory on the boundary is equal to the partition function of the theory in the bulk. That's why both the theories are same. Because once you know the partition function, you know everything about the theory. You know all the correlators, you know everything. So both theories being same is basically saying that the partition function on both sides are equal. And while computing these partition functions, these mathematical functions appear. Yeah.
Right. One of my friend from Canada is asking, any thoughts on time dilation in string theory? I'm just perhaps he wants to know, does string theory take into account time dilation or something?
Yeah, all the all the GR effects will come in string theory. So in string theory, what happens is that you have a 2 dimensional theory of these strings, and then these strings live in some target space, and the theory on the target space you get is the Einstein's theory. Actually, Einstein theory is coupled with Maxwell theory, coupled with electromagnetism and all. So whatever features GR has will be there in the target space. So yeah, time dilation, length contraction, everything will be there.
This is the last question, I think. Ma'am, can you tell the work of Ramanujan in understanding black holes and string theory, as he did those calculations in 1920s, much before development of string theory?
Yeah, so this is again related to something I did in my PhD. So basically, what Ramanujan did was he wrote down certain, there was series, he wrote down the answer for this series summations. Okay, nobody knows how he knew the answer. If he had an infinite series, he will tell you that the answer of the sum over this infinite series is this particular thing. And he has done it for a lot of series. And in particular, the series he had done it for appears in calculations of these partition functions, which are important to compute the black hole entropy. So when you compute these partition functions or something, sometimes they are called elliptic genus, when you compute these things in the field theory, these same series which Ramanujan had summed in 1920s, these series appear, and then you can just take Ramanujan's formula of that series, and then you can see that it matches the entropy. So yeah, so if Ramanujan was not there, we would not know how to sum those series, and he gave us how to sum those series.
So that means, Dr. Diksha, mathematics still rules. I mean to say, the code
Yes.
is always the mathematics, and then it comes to the observation part, etc.
Yeah,
Yeah.
yeah, yeah. Yeah.
Raghav has just one question. Ma'am, can you explain graviton particle symmetry?
Oh, what is this
Yeah,
symmetry?
I also am not being. So, Raghav, I would request you to just narrow down the question. So that is all that we have got. One thing, Dr. Diksha, I would like to ask you, because you are with a lot of researchers around in one of the best universities in the world. Now, when it comes to the question of selecting a particular research topic, say, for example, young people who are not up to it, or those who are selecting a research topic, just now you actually, told something which is called narrowing down. Now, how important it is for a supervisor as well as the student who is doing a postdoc, among the millions and thousands of topics in theoretical physics, string theory, how do we plan to narrow it down? And I mean to say, what would be the path in narrowing down a particular research topic? I think this is something very important that we should know.
Yeah. So what happens initially, for example, when you are choosing which field you are going to do, which thing you are going to do in your PhD, at that time you don't have much knowledge about the details of the field. No, you know all. For example, for me, I knew what string theory is, but I didn't know any details. I knew what general relativity is, things like this. So once you choose your PhD, the first experience is from the PhD supervisor. So the PhD gives you this thing that the supervisor will tell you a topic that he is interested in. So usually, for example, where I did my PhD, I talked to like multiple people there, trying to know what they are working on. And out of those things, what they were working on, one thing I found interesting, and I chose that person as my supervisor. But sometimes people choose their supervisor before joining PhD. Usually that happens in when you do PhD in Europe. Then it's very difficult because at that time you don't know a lot of things, and then you just make a choice. But after doing your PhD, you will start having an inclination towards a particular subfield. For example, during my PhD, I started having an inclination about understanding black hole entropy and all. Even though my PhD, I didn't have any paper on black holes. My paper were on mathematical things, but the motivation to study those problems came from black holes, because that's how motivations of Atish was to study that problem, and I found that interesting. Once you join a postdoc, in postdoc you are supposed to work a bit independently, because you don't have a postdoc supervisor. You just work, you are in the department and you work with people around in that. So by that time, so PhD you have done like 4 years or 5 years of your life, you have already narrowed down a little bit that this is the topic I find interesting. And also another thing is you keep on attending seminars and talks, and then by attending various conferences and seminars, you also understand what is going on in the market, what are the topics other people are interested in, what is the new hot topic, what is the new problem which people are facing and trying to resolve. So this also knowledge you get by attending a lot of conferences and schools, which is what I did during my PhD. I attended a lot of conferences around the world. And during your postdoc, by that time, you have already a mindset of these are the topics I am interested in. And then you find people around who work on those similar topics. And that's what even I am doing here. Even though I'm in Cambridge, there are like people working on hundreds of topics. I am interested in like two, three things. And most of the times I'm talking with those people only about those.
Okay,
Yeah.
right, right. Okay, thank you. Last two questions. I'm sorry, Dr. Diksha, there's a
Yeah,
lot of things coming around. First of all, his hand is sitting for Ms. Diksha. Thank you for taking my question. Okay, Priyo is constantly asking one thing. Ma'am, can you please explain works of Michio Kaku?
Okay, so he is like a science communicator now. Earlier, he used to work on standard model and string theory, but right now, I don't think he does any active research. At least I have not followed. I had a I had a faculty who was a PhD student of Michio Kaku, but I think Michio Kaku now shifted into science communication and all. But before that, he worked in standard model and its extensions, etc.
Physics Love is asking, hi ma'am, my question is energy conserved everywhere on a cosmic scale? If yes, then why energy theories break down on singularity point? If not, why?
So energy, when you say energy, so the thing which is conserved is T mu, which is the energy momentum tensor. Okay, energy itself, the way we work in classical field theory, is the T00 component is one component. That one component is not conserved. The full T mu, the energy momentum tensor, which has energy as well as pressure terms, etc., that thing is conserved. And for the theory, for the consistent theory of gravity, if you have why it is conserved, because T mu appears on the right hand side of the Einstein equations. Okay, so to have a consistent Einstein equation, to have that T mu should be conserved, and it doesn't break down. There are actually a lot of theorems on the positivity of this T mu also. So if there is something called null energy condition, you integrate this T mu along a null slice, and then you see that it has to have a particular sign. And these theorems were these things were used to prove this Rai-Chaudhuri equations of how JS6 come together and all. So yeah, energy by itself is not conserved, but the full thing T mu is conserved. Yeah, this is exactly the full thing. This full matrix, the covariant derivative of this full matrix is 0. Yeah.
Okay, just a second. Yeah, okay. So we won't be able to take much questions. Just one thing which is coming up from Prabhat. He's asking that how can we define energy in the domain of strings?
In the domain of strings, in the sense energy, energy is defined in string theory.
String theory, yeah. I also cannot get what it is. So Prabhat, if you can just narrow down and exactly. So energy is defined in strings, and string theory as usually takes up energy
Yeah,
as
it
a
has
whole.
a T mu tensor. You define the full
Right,
T mu tensor in string theory. So in on the world sheet theory also there is a T mu, and in the target space also there is another T mu that you can
right.
find.
So thank you, Dr. Diksha. I hope you enjoyed today's
Yeah, I
podcast.
really
I'm
enjoyed
so
it.
sorry because it was too long. Lot
Yeah.
of questions came around, and I am so happy and thankful to you that you have answered to all those questions. Thank you very much, and thank you for all the subscribers for keeping it up.
Yeah.
And any last minute message, Dr. Diksha, because you're from India now in one of the
Yeah.
best university in the world. What would be your message to the future physicist who wants to take up a career something like you?
Yeah, okay. Thanks a lot. First of all, thanks a lot for inviting me and for giving me this opportunity to talk. I really enjoyed it. I hope things were clear. Uh, and and yeah, so if you are interested in physics, if you are interested in high energy physics, this is a very long field. So for example, I'm almost 30 now. I'm still doing a postdoc. Oh, I'm on 30. I'm not even almost 30. I'm crossed 30. But anyway, this is a long field, so it takes a lot of patience and hard work. But if you are interested in it, you and anyone can do it. It's just hard work. You don't need to be very smart. It's not like only very smart people work in physics. You need to be hardworking, and and yeah, and you need to get right opportunities at right time, and whenever you get an opportunity, just grab it, uh, and good luck for your future. Yeah.
Thank you very much, Doctor, and thank you for all the subscribers for engaging in such a beautiful, engaging podcast. Dr. Diksha, I would request you not to disconnect. I will just take 1 minute of time. Thank you very much.
Yeah.
Thanks. It's a wonderful podcast. Thank you.
Thank you.